Hello, welcome to Lecture 7 for Math 155. Today I'm going to be talking to you about population or demographic models. Now this is a particular class of models that we can use to understand whether populations grow or shrink over time and how the different classes maybe within a population, for example juveniles, adults, how the proportions of those different classes change over time. And we're going to be building on what we learned last time out about eigenvalues and eigenvectors, as these turn out to be really important for solving these types of models. So in your own time, have a read for the outline for today, and let's get started. So the general type of models that we're interested in here all have the form P of n+1, so P is our vector for our population, is equal to A times Pn, where A is some matrix and Pn is the vector of our population groups or classes. Again, think things like juveniles or adults at time level n. So that time level could be the day, a week, a year, a generation. It's some increment in time. I'm usually thinking of this as being a fixed increment in time as well. This is an example of something that's called a dynamical system. We will talk about dynamical systems quite a lot at various points in this course, and we'll be talking about them in particular when we talk about differential equations. What we're really interested in here is the long-term behavior. So for some matrix A, which describes the change in population from one year to the next, what is the long-term behavior for our model for general initial conditions? Okay, so we aren't really caring about exactly what's happening for 1 year compared to the next year, given us a very specific set of initial conditions. What we want to know is, in general, given some initial conditions, which we may not know or may not be able to measure very well in a real system, what is the long-term behavior? Like I say, from that long-term behavior, the kinds of things we care about are is the population growing, is it shrinking, and if it is growing, say, what's the different breakdown of classes? So are there more juveniles than adults, or what proportion of juveniles might there be to adults? Things like that. So to get the next population level in any of these systems, all we have to do is multiply by our matrix A, which say describes things like births and deaths or aging in the population. And then we do that again and again and again. So we're iterating this process. So what we're really asking is, what is the limit as n tends towards infinity of A raised to the power of n times by our initial conditions E0. In other words, this here is our initial population or initial conditions. And seeing as we care about general initial conditions, we don't really care for the most part what P0 actually is, as long as it's probably non-zero. If it was all completely zero, then probably nothing happens to this system. So we care about general initial conditions, and we want to know what happens as we multiply this by A repeatedly on the left-hand side. So we take A to the power of n and think about what happens as n tends towards infinity. Okay, so let's consider first of all just a scalar population model, and what does that look like? So not a matrix model. So the simplest scalar population model we can think of, suppose we have a population Pn, so this is just a scalar quantity here. So this is the population at time n, and at every generation we assume that a proportion B of new members are born, new members for this population, and a proportion D of the members of the population die. So that means that all we need to do is write down P at time n+1, the next time point, is going to be the number at time n, so the number that we had before, plus the number born, minus the number that die. So we know what the value was at the time step before. It was Pn. So we have Pn plus the proportion that are born. So we know that a proportion of new members are born. So we have B times by Pn here. And we have minus D times Pn, so that's the proportion that die. So this is what our population looks like. We can simplify this a little bit by writing this as 1 plus B minus D, in parentheses, times by Pn. And since this 1 plus B minus D is just a scalar itself, we can write that as a scalar lambda times by Pn, where we've set lambda is equal to 1 plus B minus D. And then if we want to iterate this many, many times, the size of the population at time level n is going to be simply equal to lambda to the power of n times by P0. Okay, so we take our initial condition, our initial size of the population, and we take lambda, multiply it by lambda again and again and again. So we're taking lambda to the power of n, and that gives us the size of the population at time n. And we can say a few things about this. Well, we need our initial size of the population to be greater than 0. If this was just equal to 0 here, if this P0 was equal to 0, then nothing would happen. It would, if you don't start with any individuals, then nothing happens at all. We need our birth rate to be non-negative. So we can, in theory, give birth to no individuals, but we can't give birth to a negative amount of individuals. And we need the proportion that die to be between 0 and 1. So we can't have more individuals dying than are in the population at that particular time point. Okay, so if we think about these two things together, points 2 and 3 here, then we end up with lambda, which we've defined to be 1 plus B minus D, has to be greater than or equal to 0. And therefore we can entirely understand what goes on in this model just by thinking about the magnitude of our parameter lambda. So if lambda is equal to 0, then the population dies out. So it dies out immediately. So Pn is equal to 0 for all n. So it immediately dies out at the first time point. If lambda is between 0 and 1, that means that the population is shrinking. Suppose it's halving by 50% each time. So Pn is going to tend towards 0 as n tends towards infinity. If lambda is equal to 1, then Pn is just going to equal whatever it started, so its initial condition for all n. And if lambda is greater than 1, then Pn is going to tend towards infinity as n tends towards infinity. So how are we taking lambda, a value greater than 1 to the power of n, so that will be getting larger and larger and larger. So this is a very simple population model and tells you based on the number of births and deaths whether the population is growing or shrinking, but it's a very simple model for a number of reasons. One is that it has no interaction with the environment or with other species, and we also know that many populations have different properties as they age. So they, for example, juveniles don't give birth. They may die at a higher rate than adults or a lower rate than adults, depending on a particular system. We might have individuals that are very old. They might not reproduce anymore, or they might reproduce at a higher rate, or they might die at a higher rate. So these sorts of things might change over the lifespan of an organism. And therefore, we might want to account for different demographic properties as the populations age. We can do this using a model invented by Leslie. So these are actually turn out to be called Leslie models or Leslie matrices. And these are age-structured population models. So Leslie allowed us to model population dynamics when we have these populations broken down by different ages. Okay, so we can kind of take a similar approach to what we had before with our scalar model that didn't have any of this breakdown over different ages. And what we can say is, okay, well, let's take P1, P2 with subscript n's here, all the way up to PM. So we assume that there are m different age classes, and that these guys at the top are going to be the youngest, and these are going to be the second youngest, and then all the way up to the eldest. Okay, so this superscript here is indicating which age class you're in, and then the subscript is indicating the time point that you're at, so which generation we're at. So given this setup, we can readily put together a set of equations. Everything except the first class is going to be very similar in terms of its structure. So the only difference with the first class here is that all individuals are born into the youngest class. So the equation for P1 at time point n plus 1 is going to be the number that are born plus the number that we had before minus the number that die, and then minus the number that age out. And then for all other categories, we are going to have a number that we had before. So this is just for some general age category J. We have the number that we had before, minus the number that die, minus the number that age out, and then plus the number that age in. So for example, if we're in age class 2, we would have individuals that we had in age class 2 before, the individuals that have died from that age class, the ones that have matured from the previous age class from P1, and then we've got the number that are, or the proportion that are aging out of this as well. Okay, so let's think of an example of this. Suppose we've got 3 different categories. We've got 3 different age classes or life stages in our model, where we've got juveniles, sub-adults, and then adults. And we're going to assume that, first of all, we have 11% of juveniles die at each generation, 25% of juveniles mature into sub-adults. So let's write that down. Suppose, first of all, our equation for Jn plus 1, well, we're going to take the number that we had before, so the proportion we had before was 1, and then we're going to kill 11%, so 11% die, and 25% are going to mature, so 0.25. I'm going to leave this class as well. So we're going to have this multiplied by Jn. Let's work our way down through the rest of the conditions. Okay, so each generation, 9% of sub-adults die, so let's call this equation Sn plus 1. So this is the number of sub-adults the next generation. So we are going to start off with the number that we had before. So we have a proportion 1 to start with, times Sn. We're going to have 9% die, so we're going to subtract 0.09. So this is this here. And then we are going to have 20% of sub-adults mature into adults. Okay. So we're going to subtract another 20%, and that'll be our Sn. And then if we look at our An plus 1 class, so this will be for our adults, then we're going to have 33% of adults die. Okay, so let's put this over here. We start off with all of the adults, so with the proportion 1, and we subtract 33% of adults. You might be wondering why I've set it up in this way, and that will become clear in just a moment. Okay, so that's what's going on in terms of individuals dying or maturing. How about births? So we know that sub-adults, well, first of all, juveniles don't produce any offspring, okay? But we know that sub-adults produce on average 0.11 offspring, okay? So that means that for our juvenile class, we need to be adding in 0.11 times by the number of sub-adults. And how about the adults? Well, the adults, they produce on average 2 offspring. So that means that we need to have plus 2 times by An here. So these terms here are our births. What about some of these gaps that I've left here? Well, what about, are there any JNs in our SN class? Well, we know that 25% of our juveniles mature into sub-adults, so we actually need to have a 0.25 JN here. And we know that 20% of our sub-adults mature into adults, so we need to have a 0.2. Let's move it over here actually. let's have a plus 0.2 times by our subadults here. Okay, and the final thing is we don't have any juveniles maturing into adults directly. So let's just have a 0 JN here. Ordinarily, we wouldn't write that in there, but like I said, you'll see why I've done that in just a moment. We can think about this as a vector equation, right? Or a vector equation is essentially just a special type of matrix equation. You notice you've got something times Jn in each of these equations. We've got something times Sn in each of these equations. And then we've got something times An in each of these equations. There should be a plus 0 An here as well, because there's no flow from the An class into the Sn class here. So there's a plus 0 An as well. Individuals don't suddenly become younger and go from being adults to subadults. Okay, so we could write this as a matrix equation based on this. So this is a special type of matrix called a Leslie matrix after the person who invented this type of model. And we say that a linear model, so this is linear because there's no interaction between terms. We don't have things like Jn's times Sn's or Jn squareds. So it's a linear model. Every variable has a linear coefficient in front of it. So we have a linear model for an age structure population can be written in this form: Pn plus 1 is equal to L, which is L is our Leslie matrix, times by Pn, which is our vector for the population at time n. So if we're assuming that this in general has m components, that n different age categories, and L is an m by n matrix. So m age categories gives us an m by n matrix L, and that L stands for a Leslie matrix. It doesn't have to be written down as an L. It's just written down here just to remind you that it is a Leslie matrix in this case. So for this system that we had above, well, our Pn, our population vector, is just going to be Jn, Sn, and An, juvenile susceptibles and juvenile subadults and adults at time n. Then at time Pn plus 1, well, we take our Leslie matrix. In this case, what we need to do is we need to say, okay, well, 1 minus 0.11 minus 0.25 is 0.64. So we have 0.64 Jn. In the second row, we're going to have 0.25 Jn, and then in the final row, we're going to have 0 Jn. So we're going to have here 0.64, 0.25, and 0. In the second column for the SNs, we have 0.11. And then in the second row, we've got 1 minus 0.09 minus 0.2, so that's 0.71. And then in the final row, we've got 0.2. So in the second column, we have our coefficients for the SN, so 0.11, 0.71, and 0.2. And then lastly, for the ANs, we've got 2, 0, and 1 minus 0.33. So we're going to have 0.67 for that final entry. So the final column, we're going to have 2, 0, 0.67 times by Pn. So this matrix here, all I did, if that wasn't clear, is I took the entries here for Jn, and they became the entries here. Likewise, the coefficients, sorry, for in front of Sn then become the components of this matrix in the second column, and then the coefficients in our equations for An then become the final column. So in this example, if we think about what happens if we work out from a set of initial conditions, a P0, what do we have at the next generation, P1? P1 is just going to be equal to L times by P0. Okay, so our initial conditions times by Leslie matrix L. And then if we want to work out P2, then we take L times by P1, which is just L squared times by P0. And you can keep doing this so that in general, Pn plus 1 is going to equal L to the n times by P0. So we take our Leslie matrix to the nth power. So we multiply it by itself n times to get what we get at the nth generation. So, like I said at the beginning, we're interested in understanding what happens to the long-term behavior of the system. And whenever you hear long-term, think eigenvectors and eigenvalues when we're talking about matrix equations, okay? Because our eigenvectors and eigenvalues, as we learned last time, tell us something about what happens to a system as we keep applying a matrix to it over and over and over and over again. If we keep multiplying a vector by a matrix repeatedly, then we end up stretching and rotating that vector in the direction of our eigenvector, and the eigenvalue tells you whether that's shrinking or being stretched, and you're getting pulled in that direction of your eigenvector. So the eigenvector tells you about the long-term behavior together with the eigenvalue. So if our matrix L has m eigenvector eigenvalue pairs, so remember that each eigenvalue has an associated eigenvector, then if we say this is, say, lambda 1 is our first eigenvalue, and it's associated with an eigenvector u1, and then we've got a lambda 2 as our second eigenvalue associated with eigenvector u2, all the way up to lambda m um. And recall that the equation for the eigenvalue equation that this will satisfy for each of these different pairs is going to be our matrix L times by whatever eigenvector we're interested in is going to equal the associated eigenvalue lambda j times by that eigenvector. So all of these different pairs will satisfy that formula. And suppose we've ordered them so that lambda 1 is the biggest, this is bigger than the absolute value of lambda 2, and this is greater than or equal to, that should be. This is greater than or equal to absolute value of lambda 3, and so on, all the way up to absolute value of lambda m. And there's also a way in which we can write down, for most cases, and all the cases that you'll be seeing, any vector as a linear combination of our eigenvectors, okay? So if we just take coefficients C1, C2, and so on all the way up to Cm, we can write our initial condition as C1 times by U1 plus C2 times by U2 plus, and so on, all the way up to Cm times by Um. You don't really need to know why we can do that. Just sort of take that as a given for the purposes of this course. This is all based on sort of slightly more hardcore linear algebra that you don't need to know about. Okay, so what this line here is essentially saying is that we're solving P0, our set of initial conditions is equal to a row vector of U1, U2, and so on up to UM times by a column vector of those coefficients C1 and so down to Cm. Okay, that's just a brief aside. So we can iterate our equation. So P1, remember, is equal to L times by P0. That's just our Leslie matrix times by our set of initial conditions. And we've just defined P0 in terms of these C1s, these coefficients, whatever they happen to be, and these are our eigenvectors. So we have some linear combination of our eigenvectors. So L times by C1, U1 plus C2, U2, and so on all the way up to Cm times by Um. And because this multiplication is distributive, we can just take out each of the coefficients on the outside and put the matrix on the inside, if you like. So this is just the same as writing C1 L U1 plus C2 L U2, and so on, all the way up to Cm L Um. And we know from above, up here, that L times by any of our eigenvectors is just the associated eigenvalue times that eigenvector. So that means that we can write each of these bits here as C1. Now L times U1 is just going to be lambda 1 times by U1, plus here C2 times by lambda 2 U2, plus, and so on. So this is just from that equation above, Cm lambda m times by Um. This one here substituting that in. Okay. So if we do this repeatedly, if we want to work out what Pn is rather than just P1, now Pn is going to be L, change color again, L to the power of n times by P0. So this works out ultimately to be C1 times by lambda 1 to the n times by U1 plus C2 times lambda 2 to the n times by U2. So again, we've got this combination of our eigenvectors and our eigenvalues. So we're taking each of our eigenvalues to the power of n because we're applying L n times, and then multiply by some coefficients, which we don't really care about here, and also the eigenvectors themselves. Okay, so we assumed above that lambda 1 was our largest eigenvalue. So that means that all of these other terms here, when we take them to the power of n, they get small relative to this first term here. So this first term here dominates the system. So it dominates the system because lambda 1 is the largest eigenvalue. So if you take something slightly larger than lots of other things and take them all to the power of n, the one that was the biggest to start with is going to ultimately dominate the system because you're taking a larger thing to a very large power. Okay, so in that long-term behavior as n gets large, we can say that our Pn, our population, is going to tend towards C1, this should be a vector, C1 lambda 1 to the n times U1. Okay, so all the other terms we can essentially drop. So just to clarify why that is, if we again take our Pn from above, so this is just this equation here, so Pn is equal to C1 lambda 1 n U1 plus, and so on. I'll jump straight to the final term here, Cm times lambda m to the n times by Um. If we take out a factor of lambda 1 from all of these, lambda 1 to the n, then we're going to have lambda 1 to the n, just take that out, divide everything inside the brackets by that. So this first term is going to be C1 U1. And then the next term is going to be C2 times by lambda 2 over lambda 1 to the power of n times by U2, and so on all the way up to Cm times by lambda m over lambda 1 to the power of n times by Um. Why do we do that? Well, this here is going to be less than 1, and all of these coefficients afterwards are also going to be less than 1. We're taking something less than 1 to the power of n and letting n get very, very large. That means this is going to tend towards 0. This is going to tend towards 0. All of these terms are going to tend towards 0 as n tends towards infinity. So again, thinking about that long-term behavior, as we let time go very, very far into the future, all of these other terms here, from C2 onwards up to Cm, they're all going to tend towards 0, and you're essentially just going to be left with something that is approximately given by this first term here, C1 times by lambda 1 to the n times by U1. Okay, so this is how we're able to get to this expression up here, that when n is very large, so this should be as n tends towards infinity, so as n gets very, very large, Pn is going to tend towards the system given by, that's dominated by this first eigenvector, the largest eigenvalue and its associated eigenvector. Okay, so what ultimately does that tell us then? Well, if we've got an age-structured population, we can calculate a Leslie matrix for the system. So the L that we've talked about here. So we construct this Leslie matrix, which describes individuals that are born and how they age, how they die. And then we can work out what the largest eigenvalue, lambda 1, is of L, and its associated eigenvector U1. And then we're going to know from this whether the population grows or decays or tends to some equilibrium, depending on the magnitude of lambda 1. So just like in our population scalar model that we had before, the value of that lambda1 in that scalar model determined whether the population grew or shrank or stayed the same. And here, the value of our eigenvalue, lambda1 here, is going to determine the same thing. Does the population grow or decay? So it's, again, this value here is the key value that tells us what is going to be the long-term behavior of the model. So if lambda1 is greater than 1, then our population is going to be growing. And that's because here we've got Pn tends towards C1 times by lambda1 to the n. So if lambda1 is greater than 1, then the population will tend towards infinity. If lambda1 is less than 1, then the population is going to decay, so it's going to shrink. If lambda1 was equal to 1, then the population would just stay in exactly whatever proportions it started in. Okay, so that lambda1, that eigenvalue, the largest eigenvalue is really important. It determines what happens to the system. And then the eigenvector, if its entries are, say, u1, u2, and so on, and up to um, then this tells us the breakdown of the population. So what proportion are going to be juvenile, what proportion are going to be sub-adults, what proportion are going to be adults, and so on. So what proportion are going to be in class J. So we can say that our our population class at time n, population class J at time n, so age class J at time n, is going to tend towards uj, so the jth eigenvector component, over the sum of all components of that eigenvector. So this is the sum of components. And this is just the jth component of that eigenvector. So the population will tend towards these proportions. So if we, for example, if you have, say your eigenvector was 3, 1, then this suggests that your first class is going to tend towards, so if we did P1 of n, that is going to tend towards the first component 3 over the sum of the components 3 plus 1, which is going to equal 3/4. And then if I did it for the second one, so the second class P2, that would tend towards 1 over 3 plus 1, which would equal 1/4. This is all as n tends towards infinity. Okay, so that eigenvalue tells you about whether the population is going to grow or shrink, and the eigenvector is going to tell you ultimately in the long term what is the breakdown of the population going to be. So what proportions are going to be which age class. Okay. So have a look at some of the self-study questions at the end of the lecture. Make sure you're familiar with what an age-structured matrix is and what a Leslie matrix is, and yeah, see if you can answer some of these questions before coming on to the problem class. Okay, thanks very much.